Hey guys, good morning. Today, this is the AP Calculus lesson dealing with concavity. So, remember, for any function f of x, if f prime of x is positive, then f of x is increasing. I forgot what the word is. And if f prime of x is negative, then f of x is decreasing. Right? We talked about that the other day when we talked about the first derivative test for finding extreme values. If f prime of x is positive, then f of x is increasing. If f prime of x is negative, then f of x is decreasing. So if we took this like, suppose our original function wasn't f of x, but suppose our original function was f prime. If you take its derivative, you get this statement. If f double prime of x is positive, then f prime of x is increasing. Right? I'm just starting with f prime. If you take its derivative and it's positive, then f prime is increasing. If you take its derivative and get f double prime and get negative number, then f prime is decreasing. Right? So these two sets of sentences are really saying the same thing. The only difference is here we're starting with f of x, and here we're starting with f prime of x. But if you think about what this means, f prime of x is increasing. That actually means that f of x is concave up. Okay? If you have a concave up function, like this is a concave up function, right? And you look at the tangent line at points going from left to right, right? Like this tangent line right here has a negative slope. This tangent line right here has a less negative slope, which means that the derivative of this function is increasing, right? It's getting less negative. If you look at the derivative here, it's 0. If you look at the derivative here, it's positive. If you look at it here, it's more positive, right? If you move from left to right, the tangent line has an increasing slope, right? It's negative, then it's less negative, then it's 0, then it's positive, then it's more positive, and so on. So this is going to be the situation if f double prime is positive. And same thing, if you look at a concave down function, this is where the slope is decreasing, right? We have a positive slope here. We have a less positive slope here. We have a negative slope here. We have a more negative slope here. As you move from left to right, the slope is decreasing in this function. So this is the situation when f double prime is negative. This is a concave up function. This is a concave down function. Okay. A point where concavity changes from concave up to concave down or vice versa is called an inflection point. Okay. So an inflection point is a point on f of x at which two things must be true. F of x is defined and continuous, And secondly, f double prime changes sign. It either changes from positive to negative or from negative to positive, from concave up to concave down, or from concave down to concave up. So graphically, what that would look like is if you have a function, draw in a different color. If you have a function that kind of just goes like this, whatever, suppose that's the function. Inflection points are going to be points where the concavity changes. So you can kind of see like right there, the concavity changes from concave down to concave up. It also changes maybe like right there. And there's probably a point right there where it changes, right? So like if you look at this section, it's concave down. So f double prime is negative. If you look at this next section, okay, this next section is concave up. So f double prime is positive. The next section is concave down. So f double prime is negative. And the last section is concave up. So f double prime is positive. Right? So these points here are inflection points. That's what they're called. Okay, so let's do an example. Like suppose I have a function like f of x equals x to the fourth minus 4x cubed plus 10. Okay, let's analyze this function. Okay, let's first do the first derivative test. Remember, the first derivative test is to find extreme values. So I could do that here. I could say f prime of x equals 4x cubed minus 12x squared, right? And remember the process. You find critical points first. So critical points are points where their derivative is 0 or undefined or endpoints, right? Well, there's no endpoints here because this is just a polynomial, so I don't have to worry about endpoints. But there are points where the derivative is 0. There's not any points where the derivative is undefined in this case, but there are points where the derivative is 0. So I can factor out a common factor, 4x squared, and I get x minus 3. So x equals 0 or 3. Right? Those are the only critical points. These are called the critical points, remember? Right? So I could do a first derivative chart here. So my first derivative chart would look like this. I'd have my little x-axis here. I have 0 and 3. And this is f prime. And then I just need to determine whether it's positive or negative on each of these intervals, right? So if I substitute, well, this 4x squared part, that's always positive. So I can kind of ignore that when it comes to the sign chart. I really just have to look at the x minus 3. If I plug in like -1, that's definitely negative. So it's decreasing. The function's decreasing on that interval. If I look at the interval from 0 to 3, like plug 1 in, it's also negative. And if I substitute in 4, it's positive. Okay, so now I can do the second derivative analysis to determine concavity, right? So like, for example, in this case, I could just take f double prime. This would be, and here's f prime up here, right? So the derivative would be 12x squared minus 24x. And again, I'm going to set it equal to 0. I'm going to do the same thing, right? And I get x, or I get to factor out a 12x minus 2. So I get x equals 0 and 2. Now, I would have to look at the same points as critical points. Like up here, critical points are points where first derivative is 0 or undefined or endpoints, right? Down here, I also have to look at points where the second derivative is 0 or undefined or end points. Okay, so this has to include all points where f double prime of x is 0, f double prime of x is undefined, and endpoints. Now, unlike up here where these have a name like critical points, these don't really have a name. We just call them potential inflection points. They're not inflection points yet because we don't know that these are where the second derivative changes sign, but they're potential inflection points. Okay, that's what these are. These are potential inflection points. Okay, so I got to do a little second derivative chart to determine whether it actually changes sign. So I'm going to do it on the same chart that I did my first derivative chart. I'm just going to do it on the bottom, double prime. And the points were 0 and 2, so 0 is going to be right there, but 2 is going to be like here. Okay, and then I'm going to do the same analysis. I'm going to plug in -1. If I plug -1 into the second derivative, which is right here, I get a negative times a negative, right? If I plug in a -1 into this half, I get a negative number. If I plug -1 in here, I get a negative number. So this is positive. That's concave up. If I plug 1 in, I get positive, negative. And if I plug 3 in, I get positive, positive. So it turned out that 0 and 2 were both inflection points. So just looking at my sign chart, I can see there's a relative minimum at 3. 0, it's nothing. It decreases and then continues decreasing. So at 3 is where it changes from decreasing to increasing. And then the function has 2 inflection points at 0 and 2. And I mean, this makes sense with what I know about this function. This function is a 4th degree polynomial, and its shape, like if I just look at the sign chart, its shape is going to be like decreasing concave up, then decreasing concave down, and then increasing concave up like that. That's it. Okay, so let's identify these points. Like this point right here corresponds to where the function has a 0 derivative, flattens out for a second, and it also changes concavity from concave up to concave down. There's an inflection point, I'll be like right here somewhere, that corresponds to that. Okay, so that's that point. That's that point where it changes from concave down to concave up, right? And then this low spot corresponds to 3, where it goes from decreasing to increasing. Okay, so all the points are accounted for in this function. I think it might be helpful. Let's make a little table. We can make a little table of what the curve might look like in different situations. Like let's have it have 3 columns: f prime, f double prime, and f. So first of all, if they're both positive, this means that the function is increasing and concave up. If it's increasing concave up, the shape of the graph has to be like that. That's the general shape of the graph at that point, if it's increasing and concave up. What if it's increasing concave down? That corresponds to that shaped graph. See the difference? This is concave up. This one's concave down. They're both increasing from left to right, though. How about a negative positive situation? Decreasing concave up. Decreasing concave up would be like that shaped graph. And then decreasing concave down, this would correspond to like that shaped graph. So in a first derivative chart, when I have a first derivative chart like this, at each interval, I just have to look at like what's going on. Like in this little interval, it's decreasing concave up. Well, decreasing concave up, what does that look like? It looks like that, generally. And then I have decreasing concave down. That's this shaped graph. And then I have this little interval right here where it's decreasing concave up. Decreasing concave up again is like that. And then I have this last section where it's increasing concave up. That's like that. And you can see like that's kind of how this is broken down. Oops, you can't see it. There it is. You can see this is how it's broken down. It's decreasing concave up, decreasing concave down, decreasing concave up, and increasing concave up. Okay. Let's try another example. What about this one? Oh, by the way, the questions that they could ask you, like in this situation, in this function, they might ask you where are its relative min and max. They might ask you where is it concave up? Where is it concave down? Where is it increasing? Where is it decreasing? What are the critical points? What are the potential inflection points? And so, like, they might ask you any of those questions. So you need to be able to answer any of those types of questions. All right, let's do another one. How about if I have y equals x squared over x minus 2? Okay, so same thing. I'm going to do all the same analysis. I have y prime. It's a quotient, so it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that can be simplified. This would be, I'm going to just FOIL this out or distribute. So it's, I get 2x squared minus 4x minus x squared. So this would be x squared minus 4x over x minus 2 squared. Okay, so if I want to know when this is 0, I would set the top equal to 0, right? A fraction equals 0 whenever the top is 0. So this would be x squared minus 4x equals 0. I could take out an x. So x equals 0 and 4. But I also want to consider points where the derivative is undefined, and the derivative is definitely undefined when the denominator is 0. So I have to include 2. So these are points where the derivative is 0. And this is a point where y prime is undefined. I have to include both those as critical points, right? So my first derivative chart would look like this. I have y prime broken up at 0, 2, and 4. And again, I just want to determine whether it's positive or negative. So the denominator I could just ignore, right? This is y prime right here. So the denominator I could just ignore because it's something squared. I only have to think about the numerator, but this is like a simple factored version of the numerator. So if I plug in -1, it's a negative times a negative. If I plug in 1, it's positive negative. If I plug in 3, it's positive negative. And if I plug in 5, it's positive positive. So that's what my first derivative chart looks like. So just looking at this, like I can see there's a relative maximum at 0 because the way that the sign chart is shaped, it kind of goes like that, right? So there's a maximum at 0 and there's a minimum at 4. Now 2, it's not like this situation where it's decreasing and then flattens out and goes like that. It's not this situation because I know that the function itself is undefined at that point. There's actually an asymptote there. Okay, so this curve probably looks like this. Here's 2. The curve probably looks something like this, where there's a maximum over here, and there's a minimum here, and then at 2, there's an asymptote. It's not this. It's not this curve. It's that curve. All right, but let's just continue this process. So now I'm going to take y double prime, and I'm going to use this derivative as like what I'm taking the derivative of. This y prime is what I'm taking the derivative of. So this would be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And I can't see anything because my lights just went off. Just 1 second. There, they're back on. All right, so same thing. I'm going to I want to still determine when this derivative, the second derivative, is 0 or undefined or endpoints, right? Definitely it's undefined at 2. I can see that, right? But to determine when it's 0, let's see what's going on here. What can I do? I mean, look, I can factor this piece of it right here. It factored, let me use a different color. So this piece of it right here factors as 2 times x minus 2, right? How's that helpful? Because now I can see there's common factors. I can see there's an x minus 2 here, right here. Actually, let's just do this. There's a 2 times x minus 2 and a 2 times x minus 2. Let's just do it that way. Forget this one. All right, so if I factor out that 2 times x minus 2, what's left? I get 2 times x minus 2, all right? What's left on this side is the x minus 2 squared, which is x squared minus 4x plus 4. And what's left on this side is the minus this stuff. So it's minus x squared plus 4x. Cool? Now, this is nice because the x minus 2's cancel, the 4x's cancel, and I just have that, right? So this is really just 4 times 2. This is 8 times x minus 2 over x minus 2 to the 4th. And those can reduce. This is 8 over x minus 2 cubed. So x equals 2 is actually the only critical, or not critical point, but the only potential inflection point, right? Because there's no points where this is 0, because the numerator is never 0. It's undefined at 2, right? Because that's when the denominator is 0, and there's no endpoints. So on my chart up here, my little second derivative chart, it's going to look like this. Here's y double prime. It's just going to be at 2. And if I plug in 0 or something, this is negative. And if I plug in 5, this is positive. So you can see the graph does kind of seem like it's going to be shaped like that. Okay, it's concave down and it's concave up. And I can answer any of the questions about this function that I want now. Okay, so it's basically the same analysis that we did with the first derivative. We're just doing it with the second derivative. Let's try one more example. How about something like y equals 12x to the 2/3 minus 4x. I don't know what this one looks like, but let's do the same process. Okay, so the first derivative would be y prime equals 12 times 2/3 is 8 x to the negative 1/3 minus 4. Right? This marker's hard to see. So if I set this equal to 0, this would be, I could factor out a 4, and I get 2 x to the negative 1/3 minus 1. So if I set this equal to 0, that's never 0, so it's just this piece. This is 2 over x to the 1/3 equals 1, if I set this equal to 0. So x to the 1/3 equals 2, and x equals, if I cube both sides, 8. Right? 8 is the number that's going to give me 0. And you can confirm that up here. Like, this is really just, if you plug 8 in here to the negative 1/3, that's 1/2. So 8 times 1/2 minus 4. That's definitely 0. So my first derivative chart would look like this. I'd have y prime, and 8 is the only critical point. Well, that's not quite true. 8 is the point that makes this 0. 0 is a point that makes this undefined, right? Because this is a fraction. This is 2 over x to the 1/3. So I have 0 and 8. Okay? And then just determine whether they're positive or negative. Like if I plug in negative 1, for example, this is going to be a negative. If I plug in positive 1, this is going to be 2 minus 1, which is positive. And if I plug in a million, it's going to end up being definitely positive. Oh, is that true? I don't know. A million, that's a bad number to choose. Let's try 27 because it's a cube root. It's a perfect cube, rather. This, if I plugged in 27, this would be 2/3 minus 1, which is a negative number. Okay? There's the first derivative analysis. For the second derivative, y double prime would be negative 8/3 x to the negative 4/3. And that's it, which is negative 8 over 3x to the 4/3. It's never 0, but x equals 0 is a potential inflection point because that's a point where this is undefined, right? So we have 0, y double prime. And if you look at this, it's actually always negative. The bottom's always positive because it's something to the 4th power. The top's always positive, but then there's this negative out front. So this is negative, negative, concave down in both cases. Okay, so this function is going to look something like this. I have, if you plug in 0, you get 0. So it's going to be like concave down decreasing, and then concave up, or concave down increasing, and then decreasing. So something like this. And this is going to be like at 8. That's kind of what the function looks like. Okay, and you can confirm that on a calculator or whatever. So that's it. You can be able to determine now when a function is concave down, concave up. You can find points of inflection. Okay, have a great day. Thanks for watching, and I'll see you tomorrow.